So if we took a look at water, what information, or sorry, H2O, what information do we get out of that? That we have 2 hydrogen atoms and 1 oxygen. Okay, and at this stage, we're just saying atoms. We're saying 1 unit. Okay, we'll end up changing those units around a little bit. I would actually argue that that formula didn't really tell you that you added an extra layer of information on top of it, which was an awesome layer to add. Really what the formula told you was that you had 2 H and 1 O. Keep it simple. What does H mean? Hydrogen. What does O mean? Oxygen. So you know that because you've started to memorize some of the elements on the periodic table. You are responsible for having some of those memorized. Work on that. Okay? If we push through some of these other ones, okay, which is what I started to do and then got sidetracked because it wasn't actually correct, if we looked at this formula, okay, you'll notice that it holds kind of a different pattern from, say, the other 2 on the right. What's different about that pattern? Or even this one? All 3 of those seem to hold to a similar pattern.
The H, one of the H's is separate.
Okay, if we look at the 3 that are sort of grouped, circled-ish, we start with C. And if we look at the one that I sort of have boxed, let's make it a blue box. Okay, we didn't start with C. Why?
The way that chemicals combine with each other?
It's the different compounds. What we're trying to represent by changing how we look at the formula is trying to represent some information about the chemistry of that molecule, what it can possibly do. Okay? Because if we just look at the formula, we remove a lot of information. Okay? If we look at the components that make us humans, hearts, livers, rib cage, okay? If we just look at a random pile of those parts, it's not particularly easy to understand what the function is, or is that even human? Okay? We have to put it all together to see the organization to say, oh, I would guess that this pile of bones would walk upright because of how all those pieces fit together. And that's what? An archaeologist, anthropologist, an aologist does this. Okay? We're doing the same kind of thing when we look at chemistry. We want to know something about how those atoms are arranged because that gives us some information about the functionality of those. Okay? That is largely organic chemistry when we start to tier up and look at that structure. When we're in general chemistry, we tend to ignore it. Why? Because most general chemists think structure is too difficult to work with at the same time that you're working with all the numbers and conversions that you'll be doing, which arguably is a valid point. Okay? It is too much to stress about. So when you look at general chemistry, what we do is look at our formulas. We don't care about the structure or really the function as much. We're just kind of saying it does this. And when you naturally ask why, we tell you, don't worry about it. Do the calculations associated with it. Okay? As you move through chemistry, we then start to change our focus. Organic chemistry is now looking at that structure. How can we predict something about the reactivity? Okay? Which is why I'm an organic chemist, because I hate numbers. I do horrible with them. Okay? So organic is about the structure, general chemistry is about the numbers. So don't panic too much about where we organize individual things when we're looking at them, say carbon, then hydrogen, then oxygen. Okay? Or in the second case, we went carbon, hydrogen, oxygen, hydrogen. Or even in that other case, carbon, oxygen, hydrogen. Or even in the blue box, hydrogen, carbon, hydrogen, oxygen. The order isn't as important at this point. What you need to be able to acknowledge is what does it mean. In each of those cases, it's meaning the same general idea. If I try to determine the number of carbons, okay, for now my blue circle, how many carbons are in that blue circle? 2. I have 1 here and 1 here. How many hydrogens? Okay. A little bit of trouble there. We've got 3 from that hydrogen, and we have 1 at the end that I kind of crossed through. So what you're doing is just looking at the symbols, adding them up, and coming up with a total that comes out of it. Okay? Sometimes we show structural information, sometimes we don't. Be nice if we were consistent, but to be consistent, we'd have to teach you more, and we decided that it's not worth it. Okay? Which you should be thankful for. You should appreciate that, actually. Okay? We then layer even more information on it, because if we move to that last format, what are we showing there? We have an equation now. It's not just letters and numbers, but we've also introduced a mathematical symbol, and we also have a fancy little arrow in there. Okay? All we're trying to show is how a reaction occurs. We're trying to break apart those individual pieces. As we move through, we'll start to layer in what that information means. Kind of make sense? Okay. Now to the next fun one. Chemical and physical properties. We want to come up with some way to be able to look at a substance, or for that matter, a reaction, and classify it as a physical property or a physical change, or a chemical property and a chemical change. Okay? We run into big issues almost immediately with this. This class is chemistry, where you are learning about what makes chemistry. And yet one of the very first things we throw at you is we now say you have to identify chemical properties. Well, what are chemical properties? The things that make up chemistry. You don't know chemistry yet. Okay, so we're in a very kind of cyclic loop again. What we're trying to do is introduce these ideas, get you to think about them, and start to qualify kind of your extreme cases within these. And then we'll start to build as we know more and more. We can say, now I know why that's a chemical property. Now I know why that's a physical property. Okay? Some examples of just straight up physical properties. Okay? A phase. Being a solid is a physical property. Being a liquid is a physical property. Being a gas is a physical property. The color of that species is a physical property. Okay? Densities, solubilities, conductivities. Okay? A lot of the E's. When we move into chemical properties, this one gets a little bit bizarre. Because the physical properties say it's a state, we look at it, we define it, there it is. And yet when we look to chemical properties, we describe what? How a compound changes. Okay? That's a really big distinction out of the gate. Physical properties, boom, there it is. Chemical property is, boom, now what does it do? Okay? So what we end up looking at is less at a chemical property and more at a chemical reaction. How does it change or respond to the environment it's in? Okay? And that's very commonly how we reference our chemical properties, is what happens to it when it's mixed with something else. Because what we are doing is changing the chemical bond. Oh, there again, I did it. Okay? I described a chemical property by using the word chemical in it. That doesn't work. Okay? But that's what we're looking at. Okay? What happens when I bring two elements near each other? How do they interact? That is a chemical property. Okay? So what evidence could we look for a chemical change? Okay, so we've got three different conditions here at the bottom of the slide. Okay, as a kind of big hint, all three of these represent a chemical change. What do you observe in those to suggest a chemical change has occurred?
Color change.
What's that?
Color change.
Color change. Where do you see a color change?
The C1.
Okay, we look at the very end. We have a color change over here. Okay. We're starting with a clear solution, or actually technically two clear solutions, and we end up with this yellow unclear thing through the middle of it. Okay, that is a color change. Yes, we had a yellow clear solution, but we're looking at the opacity? Opacity, that sounds better. Okay, of our solution. Okay? That has changed here. So we have a distinct color change there. Okay? Does that mean all color changes are chemical changes? Nope. Okay? What makes it a color change is that, or makes it a chemical change, is that we are changing the chemical bonds within those two solutions to make a new species. If I add food coloring to cake frosting, did I do a chemical reaction? No. Right? It seems a bit weird. It's a color change. The cake frosting went from, say, white to pink.
Still cake frosting.
Okay? It is still cake frosting, and it is still food coloring. I've just mixed them into a homogeneous system. So how do I know there's not a bond change in that, but there's a bond change here?
The outcome will be different?
Check for a physical property change.
You don't.
It's not clear anymore?
Okay? You won't have a clear, obvious line and say a test question on what's going on with it. What you would have to apply is your chemical understanding to that date about what is changing within it. What is your understanding to the date about what is happening within those? Rhymes with hero. Zero. Yeah, it's a bit unfortunate. Okay? But what we're trying to do is introduce you to these examples. This is one of the reasons why it was difficult to process and build chemistry. Because we can come up with an example where we say, okay, I'm going to define this as a chemical change. And then somebody else comes along and says, well, I found something that does exactly what you're saying, but I don't think it's a chemical change. Okay? So we have to constantly keep refining and narrowing down further and further to the root of it to figure out what's happening within those. So what we've got are these overarching ideas, and that we hope most cases are quote-unquote obvious. Okay? As we'll find, I will intentionally throw examples at you where they aren't obvious, and you can debate them. Okay? And that's part of this process. What other things might we look for? Heat is given off. That's an interesting one. Where do you see that? In the second one. Okay, where do you feel that heat in that second one? Kind of being a jerk on that. It's okay. You can call me out for it. Why do you think there's heat there? Okay, we're seeing smoke. Where there's smoke, there's fire. You can even see potentially some flame there. Yeah, we're getting some heat. Okay. So a temperature change is typically a signifier for a chemical change. Okay. So let's throw the counterexample. Take a pot of water, put it on the stove, turn on the oven or the stovetop. What happens to the water? It gets hot. That's temperature change. Chemical or physical? Why is that physical? It's still a temperature change.
Does water changing state?
How do you know it's not changing state?
You didn't add anything to it? Doesn't it boil and make more?
You're right. You're all right in that it is a physical change. But the question becomes is why does that temperature change not count? And yes, you're saying, well, it doesn't change the state. How do you know it doesn't change it?
Still water.
How do you know it's still water?
It's obvious.
It's obvious. That's a fun one. Which is our standard answer, but I kind of want to avoid doing that. How might we say that that physical change in temperature is still keeping it as water?
You didn't do anything to affect its chemical bond, I guess?
What happens if we cool it down? It's still water. How would we know that?
Right.
We test some poor sap with it. Say, hey, drink this. Oh, he didn't die? Okay, well, I don't think anything changed to it. Okay? So we have to go through these tests to verify it. Okay? And in this case, you're right. Okay? If we just put the pot of water on the stove and we turn on the stove top, the water does get hotter. And that's a physical change. Okay? Why is this temperature change a chemical change then in this case? Where did the energy come from to make this sample hot?
Reacting with something else.
I took two chemicals, I put them together, poof, it's hot. How did I get the pot of water hot? I added the heat. A typical signifier for a temperature change being a chemical reaction is when you do not supply or remove the heat. If you've added the heat, okay, or removed the heat from the sample, you're now forcing a physical change on it. You did that, not the chemicals. Okay? So what we're looking for is those changes and saying, did I make that change or did the chemicals just kind of do that because I put them near each other? Okay? What's happening in the very first one and arguably in the second one? Production of bubbles is where I was going. Technically, it is dissolving at the same time. So production of bubbles, what are we looking at? A gas shifting from a liquid to a gas. I see it just a sec. So we've got phase change. Okay, and while you guys are thinking about phase change, and the counterexample will come up with that, let's go to your question.
Okay, can you repeat it? Is it a physical change if you add something to it?
If you add or remove heat or energy, you're looking at a physical change. If your temperature, your energy changes occur just based on the chemicals themselves doing whatever they're doing, that's chemical. Phase change. What's my counterexample?
That it could be just like from water to evaporating, but it's still water.
Take the pot of water, put it on the stove, we turn on the heat, heat it up long enough, eventually what happens to the water? It bubbles and turns into a gas. Did it change to be something other than water? How do we know that? If we trapped that gas and cooled it down, and we had some poor sap drink it, they're still alive, it's still water. Okay, all we did was change the phase. Okay, that is a phase change, water to a gas. Why is that one physical and not chemical? Where did the energy come from to initiate the phase change? In the pot of water, I supplied the energy to cause the phase change. And the phase change in the example shown on the board, what supplied the energy? The chemicals themselves mixing with each other. Okay? Eventually we'll get to the point where we can start to draw out what reactions are occurring at that molecular level, but we aren't there yet. Okay? So, 3 primary categories. Your textbook classifies that as 4 for some reason. Phase change, a change in temperature, either up or down, and a permanent color change. Okay? Those tend to be our standard classifications for chemical changes. And as we already discussed, we have exceptions to every single one of those. Okay? That's where your interpretation and chemical understanding needs to come into play. Questions on that? Okay. So what we're going to go ahead and do then, we'll look at some examples here.
Yes.
It was always fun. Well, for me. Let's try green. Melting ice. What do we think? Physical or chemical? It is physical. We do have a phase change when we melt ice. We are going from a solid to a liquid. Okay, but how did we go from the solid to the liquid? You had to supply heat. Okay? And yes, just by putting ice on the countertop in this room, we are supplying heat. Room temperature is providing enough energy to cause that transition to occur. We supplied that heat.
Well, wouldn't it count on the, like, because, like, what if it's you're going from, like, a snowy day to it going to somewhere and the ice melts, that wouldn't that be chemical?
It's still physical. Where did that energy come from? So now we're trying to figure out where our energy reference is. It's coming from our sun. We're exposing it to that. We are allowing that energy to come in from a different source. Okay? By the same token, if you were going to bake your cookies, could you bake cookies in an oven? Yeah, you turn on the oven, it heats up. Okay? Could you bake your cookies in your car?
In Arizona.
In Arizona, that's fair game. But aren't you doing the exact same thing? You are still exposing heat to the cookies, allowing them to cook. Okay? So what we run into a question on is system versus surroundings, which, believe it or not, is an exceedingly dicey topic that if you want to worry about it, that's way further on down the line. So don't stress too much on that. Realize that if we are going to supply energy, what we're saying is we're taking whatever our temperature is for our sample, and we are maintaining that temperature. So for ice, we're looking at 0 degrees. We are maintaining 0 degrees. If we vary off of that temperature, we are supplying it or we are removing energy. Okay? So the melting of ice is going to be a physical change. One possibility that was dressed up here for a different example is what happens if I then cool that liquid down.
Becomes ice again.
Becomes ice again. So one of the things that we can use as kind of a qualifier, I'm starting to regret picking green. Are we okay with green as a color up there?
I can barely see it. There we go.
Okay. If we have an easily reversible process, that tends to help us qualify it as physical. What is easily reversible? You threw in another caveat now on what is easy. Okay. Some of you will find this class incredibly easy. Some of you will find this class incredibly hard. Does that make the class easy or hard? It's all dependent on the observer. Okay. Dissolving sugar.
Physical.
I like the unanimous decision there. It is physical. Okay. When we dissolve sugar, we are going through a phase change. We're taking the solid sugar, our solid white powder, and we turn it into a liquid clear solution. If we wanted to get that solid white powder back, what could we do?
Evaporate the water.
Evaporate the water off. We've got something reversible. Okay? So that is roughly within our bounds for a physical change.
Are all physical changes going to be reversible?
Most physical changes are reversible. Okay, it is one of our qualifiers that makes it easier. Burning wood. Chemical. Chemical through and through. When we're looking at the burning of wood, we are taking organic matter, carbons and hydrogens. We react them with oxygen to produce CO2 and water. When written out in this formation, does that make it a little bit more obvious that we're looking at a chemical change? Yeah. We are changing how those individual atoms interact with each other. By changing those arrangements, we are changing the chemical bond. Changing the chemical bond, hallmark of chemical change. Okay. Dissolving salt. Well, since it was unanimous, it's chemical.
What?
We'll come back to that one. Mixing red food dye with white cake frosting. This is our physical. The last one is a picture image. We're starting with some yellow crystals that become purple. Okay, this one is a harder one to pick out, but this one is a chemical change. That chemical process is happening by exposing the sample to UV light. Anybody had those what are those things on your face? Glasses? Your nose? Glasses that when you go outside into the sunlight, they change color, or at least heard of those.
Yeah.
What's happening? Not polarized. That's a different process. This is an actual change in color. Transition lenses, it's these molecules that do that. Is that process reversible? Yes, it is. Is it still a chemical change? Yes, it is. How would you know? You know something about the chemical process or the process that's happening. You've looked in or zoomed in enough at the actual reaction to know that there is a significant chemical change occurring, and that's why we're seeing that color change. Okay. How would you know that? You have to spend enough time studying it. Okay. So we come up with our initial observation, say chemical or physical, and then we have to go through and prove it. Okay. So back to the fun one, dissolving salt. You all told me physical. Check the internet. It's about 50-50. Half the internet tells you it's physical, half the internet tells you it's chemical. Ask your chemistry instructor in lab. Why not? Put them under the gun, see what happens. Okay? Wouldn't be surprised if we get a 50-50 response there on chemical versus physical. Okay? Here's the issue with chemical and physical. The way we've just presented it, and for those of you that have read the textbook already, probably see it as when you look at a response or any kind of observation, it is chemical or it is physical. How many boxes are there?
2,
2. How many boxes are there really?
3,
Try again. Try again.
1.
Infinite. There's an infinite amount of boxes in this. When you look at the rainbow, what colors are you told are in the rainbow? Roy G. Biv. Interesting that you all said that. So in the rainbow, there's no magenta. What's the other thing you're told that is in the rainbow? All colors are in the rainbow. Why'd you tell me Roy G. Biv? Because if we told you to remember magenta, what's the next? Violet, indigo, blue, teal, cyan, greeny, bluey, okay? That's going to be way too hard for you to define or memorize. So what did somebody come through and do? Well, somebody went through and said, this is red, this is orange, this is yellow, this is green. Well, it's not really green. No, it's green, right? Somebody arbitrarily put a stamp on it and said, these are the colors that we have. This makes it easier for us to control and put boxes around. When we're looking at chemical and physical changes, it is a spectrum. At the red end, we have, what did I draw it as? Physical. At the purple end, we have chemical. Some processes, or processes, however you want to look at it, say melting ice. If we look at our, how do I want to do that? Let's just, that didn't work. There it is. If we look at melting ice on our spectrum of chemical to physical, it sits pretty squarely, whoops. My chemist, not an English reader. Englishist? Linguist? Our melting ice sits pretty squarely on the physical side. Dissolving sugar sits pretty squarely on the physical side. Burning wood sits pretty squarely in the chemical side. Dissolving salt, pretty much dead in the middle. Okay? So how do you qualify it? Well, it depends what you're looking at for that individual process and what you know about what is happening. What happens when you take salt? So what is the formula for salt? Let's clear it all. NaCl. When you dissolve it in water, what happens?
It becomes salt water.
Fair enough. It becomes salt water. Anybody have any ideas? We could try to draw an equation for this. What's that?
NaCl and water.
So that's an initial thought process, which isn't a bad one, but something more happens.
Changes the formula chemically.
It becomes sodium ions and chloride ions. Do I have a bond between sodium and chloride anymore? There is no linkage between them, which then means chemical change. Depending on do you know that is happening or not, you would be able to answer that question appropriately. What makes this even further kind of an obnoxious question to throw at you? Describe salt. Don't tell me salty. I don't want to know how it tastes.
Crystal?
Crystalline. What else can you give me about it? White,
Clear.
crystalline, solid.
Compound.
Compound. Fair enough. Describe sugar. A white crystalline compound. We take a white crystalline compound, we add it to water. In one case, it's a physical change. The other case, it's a chemical change. How do you know that by looking at the exact same thing happening? You don't. You would have to run other tests to test for what potential things are actually happening at the microscopic or even nanoscopic scale. Okay? At this stage, you're still learning and building with that. But that's what you need to be keeping in mind as we go through and look at examples of chemical and physical change. Okay? What do we think? Close enough? Okay, I'll accept a size, yes.
What do, if that's what you, if this is a chemical change, what do others argue for making it physical?
Physical change, because how do you get salt back from the salt water? You evaporate the water. You do the exact same process you did to the sugar water. It's an easily reversible process. That's one of the caveats that we signify for a physical change, is that it's reversible. Dissolving salt in water is reversible. You can boil off the water. Okay. So that's one of the aspects that tend to put people in the physical camp. Chemically, it absolutely is a chemical change. It's that easily reversible thing that becomes questionable. And there was another statement?
I just asked, is it both then, or?
So when it's classified on that line, you could really classify it as both. Okay, you could say, depending on your perspective, you are looking at a chemical or a physical change. Yep.
You're neither right or wrong, but
Yeah, it would be a crappy question to ask on a test, wouldn't it? Except you all now know what is the process of dissolving salt. It's officially a chemical change, and how do you know that? Because we just walked through and explained that it's a chemical change. Okay? So, not a particularly pleasant question. I don't think I would ask that. But that's the idea that you need to be thinking about when you approach these questions. Make sense? Okay. Let's go to a little more black and white stuff. Let's get some physical stuff. Law of conservation of energy. This is a fun one. We can convert energy from one form to another, but we can't destroy it. Okay? Quite as simple as that. Law of conservation of energy. There are 6 common forms of energy. Those 6 common forms are known as kinetic. Okay, potential we could throw in there. Elastic is a type of collision where we don't lose energy. Light.
Thermal.
Thermal. Heat.
chemical?
Thank you. Chemical change. Okay, physical, which is going to be our sum of our kinetic and our potential. Yeah. San Onofre, what's the one that's really close? I think it's San Onofre.
Nuclear?
Nuclear energy. Okay. We've got a variety of sources of energy: heat, light, chemical, electrical, mechanical, and nuclear. Okay. The physical one, typically it's classified as mechanical. That's where your kinetic and your potential usually slide into, is with your mechanical. Though you can potentially get, yeah, that's a dicey statement. Okay, so we've got these major forms of energy. We are allowed to convert between them, but we can't lose that energy. So if I start with 100 arbitrary energy units, I can convert that energy into different forms, but I can't destroy it. It doesn't just disappear. Okay? This is actually one of the reasons why we have problems with our energy storage and consumption today. Most of our energy comes from gas or from chemicals, okay, petroleum. We're generating that energy, and then we try to use that somehow. Well, how do we typically use our gas energy? Burning it where? Plant, fair enough. How'd you all get here? In a car. Okay, so we're taking chemical energy in those oils, and by reacting them with oxygen, we can release that energy in what is actually a rather massive explosion. Okay, and we take advantage of the energy of that explosion to cause a mechanical change, the piston to move. We then translate that piston moving into more mechanical energy that causes our car to move forward or backwards, depending on which way you want to go. Okay. Or technically left or right. But, okay. We also take advantage of that chemical energy in our bodies just existing right here. Okay. What is our chemical energy storage molecule? Some of you have had bio. ATP. Adenosine triphosphate. Oh my God, it's the most dangerous chemical ever. Just like gas, it'll kill you. Yeah, it will kill you. It also helps you live. Okay? Just because the name sounds weird doesn't mean it's all of a sudden dangerous and toxic. Okay, we're trying to describe something about it. Okay? So in our mechanical energy, say with a cannonball, that's a good example, segue into dangerous. We take gunpowder and we explode that gunpowder in a very violent reaction, which causes the cannonball to move. And it moves with enough velocity that we can go through and destroy stuff or just launch stuff. We're just having fun. Okay? And a car engine, we're doing the exact same thing. And depending on the number of cylinders in your car, you might have 3 mini cannons or 4 mini cannons or maybe 6. Anybody have 8? 12? Just curious. Okay, so we're sitting in that 6 to 4 range. Okay, it's cheaper. Probably one of the reasons why we're in that 6 to 4 range. Okay, we've got those tiny little engines with our little cannon pistons. We jump gas into those little piston areas. We ignite it. It explodes. It causes the piston to move. The natural motion of the piston will come back around, close it back down. We cause it to explode again. We time those explosions such that we can then build that cycle and we get more and more mechanical energy out of it. Okay? But it is still a continuous chemical release. Okay? If that was a perfect system, then great. We shouldn't have any real issues. We put in gas and we get out an exact amount of energy out of it. Unfortunately, we don't get a direct one-for-one transfer from our chemical energy to our mechanical energy. In almost all energy exchanges, we also generate heat. And that heat we can't control very well. Chemical energy is easy to control because I can take the molecule and instead of exploding it here, I can explode it over here. That means this point doesn't have any energy around it. Okay? So chemical energy I can control very, very well. Heat, can't control very well. It kind of just goes everywhere. We can build insulators and all that fun stuff, but it still spreads. Okay? The issue with that spreading energy, it is now a loss. Okay? I become inefficient. It is that energy loss that dooms pretty much all life. Okay? Back to that heat energy. If we go through and look at ATP, how we're actually existing, we're taking the molecule of ATP. Okay? This is adenosine. Maybe I should not point, I can draw. We've got adenosine right here. That's right, because you can see the ad and the nine and the sine all within that structure. Okay? That's because the name doesn't make sense to you. Doesn't mean it's wrong. I mean, that's what we call it. Okay, the next part is TP, which was triphosphate. Guess what that little guy is? Phosphate. That would be monophosphate. Diphosphate. Triphosphate. What happens to release that energy? We convert from ATP to ADP, the D standing for diphosphate. All we've done is cleaved off 4 little, or technically 3 little atoms, and somehow or another that releases a bunch of energy that we use for all life. 3 atoms. That's it. Pretty awesome. Massive amounts of energy stored in that bond. Okay? Thankfully, we only access it in very limited quantities, so we don't explode. Okay? But we have access to that energy, and that's how we end up forming and existing, is through that molecule. It is the energy found in that chemical bond. Okay? We can bring in some of this energy term back to our phases. Okay? I've got 3 phases drawn up there. Which phase is which? First one is solid. I like that. That is a solid. What's the next one? Liquid. And the first one was?
Solid.
Just testing. Last one is a gas. Okay? How did you know that?
Other space.
What's that?
Other space.
Something to do with the space. What do you mean?
Solids are closer to each other. Jam-packed.
How do you know that?
Or is it less stuff?
They have, solid has less room to vibrate when it's heated, and liquid has more room to vibrate.
How would you visually see that?
With a microscope.
That's a really expensive microscope. Okay. If I put a block of solid right here on the countertop, what's going to happen to it? It'll sit there. How about I take now, nobody has water handy, and I pour water right there on the countertop. What happens to it?
It's gonna spread.
Spread. So what is each of those molecules doing? Moving. If we take a look at the liquid sample, what's happening? What are they trying to show with the kind of shading? Moving. There's now more space. There is more movement in the liquid. What happens if I try to put that same amount of gas down on the table? It goes off everywhere. I can't do it. Okay, the gas is going to fill that entire volume. We could go back to our compressibility. These are physical observations you have already made. I appreciate that you're saying that I told you that. I didn't tell you that. You did that. Okay, you already knew these observations. You're now trying to draw parallels to models to represent those better. How can we tie that back to kinetic energy? Well, what is kinetic energy? Kinesiology. Any kinesiologists? I actually said that one right. That's good. What? None? Dang it. Anybody know what kinesiology is? Study of movement. Okay, so kinetic energy is? Energy of movement. There you go. The more movement we have, the more kinetic energy we have. So if we look at our three phases, which of those three phases has the most energy? Gas. Cool. So we can specify some kind of relative comparisons now off of these. What happens as we change the temperature?
Increases the movement or decreases the movement?
Okay. It's going to change how we move. If we increase the temperature, what happens? Okay. We start to move from a solid to a liquid to a gas, which is ultimately increasing the energy, or increasing our kinetic energy. What happens if we decrease the temperature? We slow everything down, and we end up removing that kinetic energy. Okay? So every phase has kinetic energy, because they are all constantly moving. Whether we perceptibly notice that is a separate issue. Solids we tend to not notice. Okay? Liquids and gases move like crazy. Yes?
But that kind of raises a question for me. So glass, super cooled liquid.
Yep.
Why is that when you add heat to it, essentially it still doesn't move any quicker?
It does. You're telling me if you take glass
Right.
and I put it in an oven, the glass just stays there?
Right.
It moves a lot more, and it starts to become molten and liquid, and that's how we get different forms of glass. Okay, we can take panes of glass, and if you take a pane of glass, you look at really old sheets of glass, you'll notice it starts to bubble at the bottom. Why?
Because of movement.
It is moving already. It's an amorphous liquid that happens to have a relatively low, it's actually called a glass transition temperature, not even a melting point. Okay? But its melting point, its transition between solid and liquid is so low that if we're at room temperature, it's kind of straddling that line between solids and liquids.
Okay.
Okay. So that is a weird, glass is a weird one because it's not really a solid, it's not really a liquid. It's an amorphous liquid that carries different properties depending on the temperatures you're looking at. Okay, kind of. Okay. So if we look at our energy and, actually, sorry. Are there other questions on that?
Yeah.
Is that a yeah?
What, do all the phases have kinetic energy?
Do all the phases have kinetic energy? Yes. Every phase moves. How much it moves is your threshold on deciding is that perceptible or not. When we talk about solids, what would we say the motion is for our solids?
Little to none.
Little to none. Okay? There's an awesome question by awesome. I really don't like it on your practice final. Feel free to open up and look at the practice final when I actually post those, which will hopefully be today, that references which phase exhibits restricted movement. Okay. Well, solids sort of have movement, but where's that line? It's a really bad question. Okay. The motion that we assign to solids is typically 0. So if you're looking at a question that says we have a phase that doesn't move, that is solid. If we have a phase that kind of moves, liquid. If we have a phase that has unrestricted movement, gas. Okay, you're looking at different stages within that, and again, we're setting arbitrary limits.
That's still considered to have kinetic energy.
It is still considered to have kinetic energy. Okay. Energy and chemical changes. When are we done? 2:15, right? We can convert our energy from one form to another. Okay? So I can take water and I can pump a bunch of electrical energy into it. And in fact, there's been big debates about doing this already. Our hydrogen fuel cars that came out a little while ago, they've kind of disappeared from popularity. Everyone's, oh, that's amazing. Cool, we can drive a car on hydrogen. It only produces water. Cleanest thing ever. Where did you get the electrical energy to convert the water to hydrogen? Well, we got it from burning fossil fuels. Wait, what? You got it from doing the exact same thing we were already doing. That defeats the purpose. You added an extra step in the process of getting that mechanical energy that we wanted. What does that extra step result in? Heat. That heat is energy we can't use, which means what happened to the efficiency of our system? It goes down. So that defeats the purpose of going through and doing that. So it comes now to where do we get that electrical energy to do this process? Okay. Ultimately, the best source would be the sun. Okay? Because if the sun stops giving us energy, we have a lot more to worry about than just how am I powering my car. Okay? But if we run out of fossil fuels, okay, that is a very real issue, and then we would then have to fight and do all sorts of other weird stuff. That would be nasty. We don't want to deal with that. So we want to come up with a different source of our electrical energy. Okay? But back to our example, we can take water using electrical energy, convert it to hydrogen and oxygen. How can I get the water back? This is fun, because we're now looking at a reversible process. Can I get that reaction to reverse? What do? I take hydrogen and oxygen and I light a match. And I get a poof. Usually comes with a quack sound associated with it too. And we get water vapor formed out of it. We can reverse that process through a relatively simple thing. What ends up happening with that big poof? Usually if someone's standing nearby, they go deaf because it makes a lot of noise. Noise happens to be a mechanical energy, sound waves. We also typically get a big flame associated with it, which tends to be releasing heat. The flame also is shown through our light energy. So all of those energies end up getting subdivided out into different categories depending on what we're looking at. We can convert between them, but we can't destroy them. I didn't like the paper towels anyway. Okay. Questions? Okay. Lower your gas bill. In terms of expense, is it better to fill a gas tank in the cool morning or in the warm afternoon? Okay. Why the cool morning? So this is a weird thing. When we're talking about filling a gas tank, we're filling it with what phase?
Liquid.
A liquid. So why are they showing a gas up here?
Because it evaporates quickly.
What they're trying to show is what we're doing in this example is pushing it to the extreme when we're looking at our temperatures. Okay, officially we should actually even throw in the solid here. If we start with that liquid and I go in at a stupidly hot temperature, what happens to the liquid? Turns to a gas. What happens to the motion? It increases, which means to hold the same number of particles, what do I need?
More space.
More space. But that's fine because your car has a giant inflatable bladder that you store all the gasoline in, right? You're driving down the road, you're just dragging this giant bladder of gas. Okay. You have a confined volume. You can only hold so much volume. If your liquid gas is turned all the way over into an actual gas, you're holding very few particles. Those particles are the ones giving you the chemical energy. Okay? So if you were going to go in to fill up your gas tank, do you want the gas that's taking up lots of volume, which means very little particles, or the one taking up very little volume, where we get lots more particles? Little volume, more particles. That's going to happen at lower temperatures. That's a solid. Okay? So the difference between our solid and a gas, and even our liquid and a gas, is drastically huge. Okay? Which is why we deal with liquids, because they're relatively easy to transport, and the solids don't flow kind of easily. Okay? So we can get more bang for our buck in the liquid than we can for the gas.
So how ripped off are we getting?
So now the question becomes, is if we fill when it's really, really cold and we're as close as possible to that solid phase as we can, how much more gas are we actually getting out of it? Well, this comes down to the compressibility of our liquid. How compressible was a liquid? It was only Thursday. Not very compressible, which meant when we change the temperature, we're saving fractions of pennies. So did I actually put the answer up here? I didn't. Your textbook has the answer in it. It's like a penny for a tank. Okay? So it really doesn't matter. Yeah. And hey, if you're scraping by on pennies, that's fine. Law of conservation of mass and energy. There's another big famous equation comes out. This is fun. Einstein says this. Energy, he was able to determine that energy was directly related to or even equal to mass. What does this mean for us? Well, if I cannot create or destroy energy, what does that necessarily mean about mass? I can't create or destroy mass either. Okay? What is C? Not the letter after B.
It's like the speed of light.
No one even laughed after I explained. That hurts. C is the speed of light. Okay, it's a standard constant. Fun little expression. That's really all you need to know out of it. You can't create energy. You can't create mass. Okay? When we get into equations, we'll run through a process known as balancing equations. The point of balancing equations is to make sure that if I start with one carbon, I end with one carbon. I can change where it's located, but I cannot destroy it. It must still be there. Okay? Oh, shoot. Yeah, I forgot that's here. So I'm going to kind of dice a little bit here because we still got 5 minutes, but I really want to hit this topic on significant digits because I want you practicing that sooner rather than later. Okay? So we'll slide through the types of measurements here a little bit and jump to our significant digits. Measurements, we got a bunch of little measurements we can do, yada, yada, yada. Ta-da! There's some more uncertainty, yada, yada, yada. I promise we'll come back to that. Mass, volume. Come back here. Significant digits. Okay. A lot of people hate significant digits. And that's because when you go through your math class, how many significant digits do you have to worry about? None. You go to your physics class, how many significant digits do you have to worry about? Probably give you some arbitrary number, maybe 2 or 3 or 4. Okay? Chemistry seems to be the only class, and I don't understand why, because we're not the only science, but chemistry seems to be the only class where we're like, hey, significant digits are important. You should pay attention to them. Okay? That said, not that big of a deal. I mean, really, really big deal. Okay, now I'm covering the microphone. Not that big of a deal. When you go through and do your problems, you will find that under most circumstances, the significant digits are obvious. Okay? That said, under these circumstances, significant digits are not obvious because we're not in an obvious situation. We're in the textbook where we're going to throw all sorts of weird curveballs at you. So if we go through and take a look at these digits, we want to identify the ones that make them significant. So if we look at that first number, how many digits are significant in that number? Whoop. Ignore that button. 1. 1 digit is significant in the number 10. If we look at the next number, 10, how many digits are significant? 2. We look at the next number, 30. 3. Next number, 2. Last number, 1. Don't we love significant digits? Okay? Significant digits have to do with how you make a measurement. Okay? How many measurements do you make in mathematics? 0. You're told numbers and you work with those numbers. Measurements you make in physics, you make a lot of measurements in physics. Okay? You should be seeing significant digit rules in physics. I don't know why nobody seems to say they learn significant digits in physics, but you should be seeing them there. Biology makes measurements. Okay? Chemistry certainly makes measurements. Engineers make measurements. Engineers should know significant digits backwards and forwards. They're like, this is a dumb thing to talk about because they already know it. Okay? That's not true. They don't. How important are significant digits incredibly important because it conveys a lot of information about the device you use to make that measurement. Okay? If you make the measurement, do you know the device you used?
Yes, you should.
Yes, you used the measurement to make the device, right? Or the device to make the measurement. Okay? You have that information already ingrained. But when you report that number to somebody else, they did not make that measurement. They don't know what you're using. Your numbers need to convey some extra meaning about that device. That is what significant digits do for you. Okay? In the lecture, you rarely have to worry about it. Okay? You're told certain numbers of significant digits and you work within those limits. Here, okay, in the lecture at the beginning, we're going to go through and look at significant digits, and you have to follow certain rules and apply those rules consistently. One pattern through all of these: the digits 1 through 9 are always significant. There is never an exception to that. If you see a 1, 2, 3, 4, 5, 6, 7, 8, or 9, that digit is significant. Okay? So we could go through and underline all of our significant digits. Each of these numbers has at least one significant digit. Okay. Is there another type of digit that we could have included? 0. So now the question is, what is 0? Is it a digit involved in the measurement, or is it a placeholder that is telling you where to put the significant digits? Because 0 holds both of those meanings, and depending on where you use it, it's holding different intents. Okay? So you have to be careful in that interpretation. Okay? That interpretation has to do with your decimal point. Okay? So digits 1 through 9, always significant. If there is no decimal point, okay, for the 0 to become significant, it must be controlled on both sides by a significant digit. Both to the left and to the right of that 0 must be a significant digit. It does not have to be immediately next to it, but it has to be next to it to the left and to the right. Must be specified. If we go through and look for the next rule, if there is a decimal point, then the 0 only needs to be immediately preceded by a significant digit to be significant. Okay? So we're kind of out of time, but I'm going to real quickly throw up the answers here, assuming I don't make any mistakes. What I would expect you to do is by Thursday, go through and either verify these or come back on Thursday and be like, that did not make sense. I think you're wrong. Be stronger than that. You're wrong. Okay? So, real quickly, 3, 2, 3, 4, 2, 2, that's a 2, 2, 3. Those are your answers. Those are your numbers of significant digits for each of those. On Thursday, you should be able to come back and say, yep, Mike, you're absolutely right, or no, you're an idiot, you messed one up, fix it. Okay? Preferably say it a little bit nicer than that, but it's okay if you do the other way. Okay?